Strong bases like alkali metal hydroxides are ionic compounds that dissociate completely in water. The alkali metal cations are stable enough in solution to allow hydroxide to exist as an ion in solution. Let's look at a different scenario where we replace the ionic hydroxide with a hydroxyl group covalently bonded to a carbon chain. Now we have an alcohol. Alkali and alkaline earth metal hydroxides are known as strong bases. Alcohols, however, can act as acids or bases. Less substituted alcohols are typically more acidic, and more substituted alcohols are more basic. This has to do with the stability of the ions produced by dissociation. If the hydroxyl group dissociates, you're left with the hydroxide anion and a carbocation. Tertiary carbocations are the most stable, whereas methyl and primary carbocations are the least stable. If a proton dissociates from an alcohol, you get the proton and an alkoxide anion. Here the negative charge is primarily on the oxygen, and every atom has an octet, so this is favorable in less substituted alcohols. Acid dissociation constants of alcohols range roughly from 10 to the negative 16 to 10 to the negative 18. Doing the math, this means that 1 in 100 million to 1 in 1 billion molecules of alcohol has dissociated to yield a proton and an alkoxide anion. Phenols are alcohols with a hydroxyl group on a benzene ring. They are much more acidic than typical alcohols, with pKa's around 10 to the negative 10. This is likely because the negative charge of phenoxides can be delocalized and shared by the aromatic ring. We can control the behavior of alcohol by adding either acids or bases. If we add hydrobromic acid to alcohols, for example, we can get alcohol acting more as a base, forming water and an alkyl bromide. This video is technical enough without explaining the mechanisms behind this, but you can look it up if you really want to. Just look up SN1 and SN2 substitutions. Since primary and secondary alcohols are more acidic than tertiary alcohols, yields are lower when those are used. Now if we add sodium hydroxide to alcohols, they act more like acids, losing a proton, forming the alkoxide anion and water. Since alcohols are weak acids, the alkoxide ions are strong bases, and with the exceptions of methoxide and phenoxides, are stronger bases than hydroxides. Alkoxide ions, however, are so basic that they are protonated by an acid as weak as water, so the water produced hydrolyzes the products back to sodium hydroxide and alcohol. Therefore, the reaction reaches a point of equilibrium rather than going to completion. This can be avoided by reacting alcohols with sodium metal instead of sodium hydroxide, thus keeping water from forming. Either way, alcohol acts as the proton donor and thus an acid. To summarize, hydroxide ions are strong bases in solution, but covalent hydroxyl groups can be either acids or bases depending on the rest of the molecule and whether acids or bases are present. Chemicals like alcohols that have both acid and base properties are known as amphoteric. Side note, I find spirit science's lack of self-awareness amusing.